Welcome to the 20th lecture for Physics 4B. We continue our illustrations of driving magnetic fields produced by different current distributions, finally introducing Ampere's law and utilizing symmetry to calculate the magnetic field in certain situations easily. Before we do that, we wrap up our discussion of magnetic field unit from last lecture. And before we properly introduce and start applying the Ampere's law, I think a comparison of highly symmetric electric charge geometries we used for Gauss's law applications and the highly symmetric electric current distributions we will use for Ampere's law applications. I think this comparison will be useful, so we do that. And we introduce the Ampere's law, illustrating the path integral and what it means for a current to be enclosed. There are 4 geometries of highly symmetric current distributions in which Ampere's law can be used to derive the magnetic fields for, and we do that. Just like with Gauss's law, again, Ampere's law is always correct, but not always useful for calculating magnetic fields. We wrap up this lecture with an overview of magnetism in matter, just to give some sense of high values of magnetic permeability that can be obtained with ferromagnetic materials. This is it for magnetostatics. Next week, we will introduce Faraday's law, which involves the situations in which magnetic fields are changing, which induces electric fields. That'll be the beginning of what we call electromagnetism. Oh, before I move on, I should talk about unit of magnetic field. How many? Because I never really talked about that yet. So how many here know the units of magnetic field? There's 2 common units that are in use. How many here have dealt anything with the magnetic field? No one here? Okay. But some things you might know. So let me write down first. Unit of magnetic field. Well, what are some of the common magnetic phenomena that everyone around the world can refer to? There's got to be something. Okay, that's so why does aurora borealis happen at all? Because you wouldn't see aurora borealis on Mars or Venus or Moon. It happens only on Earth. Of all the planets in the solar system, it happens only on Earth, and maybe Jupiter. But why? Well, but Jupiter is a gas giant. It's not a... Okay, of all the terrestrial planets, it happens only on Earth. So why does it happen on Earth and none of the other rock planets?
Because we have a magnetic field around our planet that protects us from any waves coming from the sun.
There's the geomagnetic field. There's magnetic field due to the Earth. That is something that everyone can refer to. So that would be a convenient magnetic field to refer to. And this is the unit that's convenient for referring to how much magnetic field does the Earth have. That this is like the customary unit. So we call that Gauss. Gauss is one of the convenient unit of magnetic field, named after the same guy that Gauss's law is named after. He was, he did a lot of stuff. So Gauss is defined in such a way that the Earth magnetic field due to Earth, it depends on where you are on the Earth. The strength varies a little bit. It's dipole field pattern, and it depends on where you are. But it's going to be approximately 0.5 Gauss. Yeah? So this is a respectable amount of magnetic field. It's large enough that it affects this compass. Right? So I'm not talking about some microscopic amount of magnetic field. It's enough that, wait, did my compass demagnetize all again? Yeah, I think it's fine. It's going to point to north. Okay, so it's a large enough magnetic field that it'll affect compasses.
All right. The downside of Gauss, so if you work with any kind of magnetic field, you'll see Gauss a lot. It's a very convenient unit. When my research used to involve magnetic fields, this is the unit we used all the time. But this is not an SI unit. As in, the promise in SI unit is that when you stick to SI unit, you will get really simple quantity. For example, you have this expression here, right? The promise of SI unit is that if you use ampere and meter and on SI unit here, then promise is that when you multiply this out, you are going to get Newton. That's the whole reason we have SI unit. And if we use the Gauss here, that wouldn't work. That wouldn't give you Newton. In fact, it'll give you 0.1 millinewton. So Gauss is not an SI unit. It's based on an SI unit, but the actual SI unit of magnetic field, it's some other one, that name that you probably have heard before, Tesla. So Tesla is the SI unit of magnetic field. And the way to get a sense about Tesla is that it's related to Gauss this way. 1 Tesla is 10 to the 4 Gauss. Does Tesla sound like a small or large magnetic field? Large, yeah. And do you guys know how to generate huge magnetic field artificially? Well, yeah, so something like electromagnet, like the place that uses really large magnetic fields are like a CERN, the Large Hadron Collider. Anybody here know how those electromagnets are made? They use something called the superconductors to make as much current to flow as possible, because looking at expression like this, the more current you have, the more magnetic field you can have. And I keep forgetting, I think the largest magnetic field that we can produce is something like 40 Tesla. Is that right? It might be 15. I don't know, it's definitely less than 100 Tesla. So Tesla is such a large unit of magnetic field that if somebody ever tells you about they have 100 Tesla magnet, you know they are lying, because there are no materials with the properties that can produce that large of a magnetic field. So these are the units of magnetic field. Let me just wrap it up with this one last thing. So if Tesla is an SI unit, so I'm saying that if I plug in Tesla here, that all the units will work out so that I get a unit of Newton here. So this is not one of the basic SI units. It must be related to the basic SI units somehow. So how is it related? Or how would you get at it? I mean, you could always look it up. You could say, all right, what is 1 Tesla? And Wolfram alpha will be able to tell you. That's one of the nice things about Wolfram alpha. It's unit aware, and whenever you give it a physical quantity, it actually expresses in many different ways. So 10 kilogauss. That's what I was saying earlier. This is how I memorize, get a sense for Tesla. But if you keep going down, okay, here it is. Basic unit dimensions. It says mass per time squared per current. Oops, what did I do? Mass per time squared per current. So kilogram per second squared per ampere. So if you have access to Wolfram alpha, that's all great. You would just look it up. How would you figure this out? What did I tell you about remembering units in the electromagnetism? I told you it's complicated, that I don't try to. When we are doing circuits with a volt, ampere, ohm, that's when I was telling you there's sort of interlocking web of relationships. I don't really try to memorize any particular unit in terms of other things. It's something that you're just going to end up forgetting. But there's something that I do try to remember. Well, I guess 2 things that I try to memorize. Let me tell you the first thing I memorize all my formulas. So everything I write down here, I can write it down from memory. How would this help me figure out units? So once I have this formula where I know all the units, then whatever Tesla is, it must be defined in a way that the algebraic relationship here is valid. That's the whole principle behind dimensional analysis. So once I have remembered the formula that relates the quantity I want in terms of other quantities that I already know the units of, then I can go back. I can use this formula to figure out what Tesla is in terms of these other things. So let's just quickly do that. It won't take that much effort. So it'll be, okay, force, Newton is equal to Ampere times meter times Tesla. By the way, when I do these notations, I have to tell you, I do it slightly non-standard. The standard way is actually to write these out using symbol M for mass, T for time, and current, I guess I for current. But I found that to be confusing to a lot of people. So I'm just going to use symbols for SI units, because the assumption in this class is you're not going to go away from SI units. So solve this for T, Tesla. Then you get Tesla, or rather 1 Tesla is equal to 1 Newton per Ampere times meter. Hey, that's not what I have there. But I can write out what a Newton is. Hopefully you have this memorized. Newton is equal to kilogram times meter per second squared. Now, if you don't have this memorized, how would you get at that? What would you try to remember to recall that this is the relationship for Newton? Yeah, Newton's second law. Force is equal, net force is equal to mass times acceleration. So this is force is equal to mass times acceleration. So the technique I'm telling you, you could have used it from physics 4a. It's just that only with the electricity and magnetism, unit relationships become complicated enough that if you're trying to memorize this, you'll forget it. But if you memorize this, you will always be able to rederive this. So anyways, putting this in, so it's a kilogram, meters cancel out. So I end up with 1 kilogram per second squared times Ampere. And that's what you have there on the board. And I can do one more check. I guess it's sort of unnecessary, but maybe it's useful. So this mu naught, I have it expressed in terms of Newton per Ampere squared. But this kind of obscures the fact just how important this permeability constant is in expressing magnetic field, right? So let's say I want you to express this mu naught, not in terms of Newton's and, forces and current, but in terms of how much magnetic field is going to be produced. Then I do the same thing here. I write down, all right, this is a formula that I have memorized and can use. There are other formulas that I could use, but this will work as well as any other formula. So, or if I don't have this handy, I could go back to this. But this is simpler. And the key here is that to have a recognition of the algebraic relationship that's expressed in the formula. It's the same algebraic relationship for the unit. So once you start paying attention to this, units will just come automatically. It's not something you have to put in a lot of effort into memorizing. So let me just write that down. So I have one relationship there. Magnetic field is mu naught. I'm not even going to write down 2 pi because that has no units, times current over length. So writing down all the units here. The magnetic field, we are measuring it in Tesla. That's the SI unit of magnetic field. So that should be given by, or this is actually equal now. That should be given by whatever unit of mu naught is. That's what we are trying to figure out, times unit of current, Ampere, divided by length, meter. So to figure out the unit of permeability or magnetic constant, you just solve for this algebraically. Then you get permeability is equal to Tesla times meter per ampere. So Tesla times meter per ampere. And so this unit here could equivalently be expressed as Tesla times meter per ampere. And I think Wolfram alpha is comprehensive enough that when you look up permeability constant, that should be one of the units it gives the quantity in. I mean, this is, I guess, the most convenient one, but one of the units. Henry's, I don't like Henry's. All right, okay, so it's not in the list, but this is what I can do. Permeability first space in Tesla times meter per ampere. And it'll actually, Tesla meter, okay, there it is. I had to force it to give it to me, but it does when I ask it for that unit explicitly. When you give it wrong units, it actually wouldn't give you an answer. If I say Tesla meter squared per ampere, which is not a valid unit for permeability, it doesn't actually do that. It tells me, oh, these are the actual units. What are you talking about? So, good. Any questions? So, so this is the simple numerical exercise, and what took longer is to describe all these unit relationships. And this is the last time I will explicitly mention units. Once again, with this advice that you always start out from the formula to figure out the unit. I don't even try to memorize these relationships. I'm just going to forget it. But if you start out from formulas, then you will always be able to get correct units. So I guess the burden that this places is that you have to remember the formulas correctly. In physics 4a, you could check if you memorize correct formula by doing dimensional analysis, right? In electricity and magnetism, I don't really do that because it's harder to memorize units than to memorize the formulas. So let me call this geometries for magnetic field. Before we talk about geometries for magnetic field, I want to start by recapping something that you learned in electrostatics. So in electrostatics, we started by covering Coulomb's law, which says the electric field due to a point charge Q is given by Coulomb constant times the amount of the point charge divided by r squared times r hat for direction. And you can do quite a lot with it. And in fact, when you have point charge, this gives you a very intuitive feel for electric field. But pretty soon, this becomes difficult to work with extended charge distribution. Like if you have an infinite line of charge, then you have to do integral. If you have a plane of charge, which is actually quite common, like in capacitors, you have to do double integral. So what we introduced is Gauss's law, which says the surface integral of E dot dA over a closed surface is equal to amount, let me use the coefficients we are using, 4 pi times Coulomb constant times the charge and closed. Or if you want to use constants that your textbook uses, you just replace this with 1 over epsilon naught. So you get this version, Q and closed over epsilon naught. Now, when we introduced this, it was with the intention of using it to calculate the electric field. But one difficulty that we quickly run into is that the quantity that we are interested in, electric field, is inside an integral. So, and it's not like you can take a derivative of each side to get electric field. So in order to recover electric field, we need to go through some proof argument steps to be able to pull out the electric field outside of the integral. So what we had to rely on were symmetry arguments. So we had to use a symmetry argument
And when you are using symmetry argument, you are limited in what geometries you can apply it to. If you have just an arbitrarily shaped charge distribution, there's no symmetry argument to use there. So what you have to do is you have to limit yourself to being able to calculate electric field over highly symmetric distributions. So we covered some examples of those geometries. You have lecture videos on all that. So we did it for, I guess, well, we have a cylindrical geometry. That would be a line of charge. And we had a planar geometry. That would be infinite plane of charge. And these geometries had certain symmetries that allowed you to constrain what directions of electric field can be, and that allows you to simplify this expression enough to say that electric field either comes out of the integral, or for some of the surfaces that E dot dA along those surfaces is zero. And the final symmetry was the spherical symmetric geometry. And point charge would be actually an example of that. Although with Gauss's law, you can expand it quite a bit. You can use this to calculate electric field due to a uniformly charged sphere in all the regions of space. So this is a reminder, review of what we did in electrostatics. And what I now want to say is what we will do is a magnetism version of that. So this is what you did in electrostatics. Now what we'll do in magnetism as a reminder of what we have done. So in magnetism so far, we have introduced Biot-Savart's law. We said that small contribution to the magnetic field due to a small segment of wire, current carrying wire, is given by this relationship. Ke over c squared times the current is the source of magnetic field. So this IDL is what indicates that it's the amount of current in a small segment of wire. And the direction, and there's a over r squared. Because of magnetism is still inverse square law. It goes as inverse square of distance, at least for point sources. Now, the direction of magnetic field is quite complicated. It's all captured in IDL cross r hat. This cross product works out all the complicated directions. And in lecture, you see me using Biot-Savart's law to derive magnetic field for long line of current and for loop of current. So you can watch that. And just before I move on to the next point, if you want to use the combination of constant coefficients that your textbook gives you, then this portion is mu naught over 4 pi. So that's what we have done in magnetism so far. Now, what we are going to do is we are going to be introducing Ampere's law. And as we introduce Ampere's law, it'll be very useful for us to identify geometries where there will be sufficient symmetry for us to be able to use Ampere's law to calculate the magnetic field. So what we will do soon, we will introduce Ampere's law, which says, so Ampere's law looks different from Gauss's law, although there are some superficial similarities. Ampere's law will say that the closed integral, and closed integral not of surface, but of a loop, a path, a one-dimensional integral. So closed integral of dot product of magnetic field and path element. And this path element, even though DL looks exactly like this DL, they have slightly different meanings. So this is of wire, current carrying wire. This is of what I like to call Amperian loop. So this is a kind of imaginary path that you define for calculation aid. This DL is a physical length of current carrying wire. So anyways, Ampere's law says that this integral takes a certain form that that's related to the source of magnetic field. So it says this is equal to 4 pi times Ke Coulomb constant for some reason. Well, same as Biot-Savart's law. Coulomb constant divided by c squared times current enclosed. And there is quite a bit of similarity between what you see here and what you saw with Gauss's law. So Gauss's law says that charge is the source of electric field, and Ampere's law will be saying current is source of magnetic field. Now, we will have to, because in this expression, we have the exact same problem we had the Gauss's law for electric field. What we are interested in is not the integral, the b dot dl. I don't care what that quantity that is. It doesn't hold any interest for me. What I will be interested in is the magnetic field, and that's inside an integral. So what we need is some way to get this quantity out of the integral. And in order to do that, we need symmetry argument. So in the next 5 to 10 minutes, I will identify and illustrate those geometries with high degree of symmetry that will allow us to do this exact thing. Pull out the magnetic field out of the integral, or for some sections, argue that b dot dl should be 0. So we need to identify geometries with high degree of symmetry. I think some geometries are, it's more natural to think of that symmetry. So for example, in the case of Gauss's law, we had cylindrical geometry. So I think a cylindrical geometry will still provide some high enough degree of symmetry to use symmetry argument to simplify that integral. So we'll have cylindrical geometry where some symmetry argument will have footing. And what this will look like is something like, imagine a long line of current, long straight line of current. So if you had a long wire, and I'm going to draw only a finite section of the wire, but you have to imagine that this is infinitely long for this symmetry argument to work. So let me just indicate that they don't end at the end. And current flows in some one direction. And this is one such geometry where there's enough symmetry. So when we were doing Gauss's law, cylindrical geometry had rotational symmetry about the center of the cylinder as an axis, and it has rotational, and it has a translational symmetry. Because it's infinitely long, you can translate it and not really change anything. And it had, and I think that was more or less it. With Gauss's law, we had a reflection symmetry. With Ampere's law, because the current has a direction, it won't really have a reflection symmetry. So this exhibits rotational, and I'm writing this down as a shorthand. You have to remember it's rotational about one particular axis, not any other axis. It has translational symmetry, and I think that's it. And it's useful to kind of think through what direction in general the magnetic fields are for these geometries. And this is where the right-hand rule, I think this is like the second version of right-hand rule, is really helpful. So you direct your thumb in the direction of the current, and your remaining 4 fingers, they curl in the direction of so the direction that these 4 fingers curl in is the same direction that the tangential magnetic fields are circling around the current. You can get this from application of Biot-Savart's law, and this shortcut right-hand rule is a way to remember that. So with the current flowing from left to right, at the top, the magnetic field will be coming out of the screen. So let me just draw that. you at the top you have magnetic field coming out of screen. It wraps around in a circle, and at the bottom the current is going into the screen. So this is a circular kind of magnetic field. So this is the general sense of the magnetic field, and it wraps around. And it's because of the translational symmetry, this as you move about along this cylinder, the strength of this magnetic field doesn't change. So that's one geometry, and there's a quite close analog to geometries we've used for electricity. And we have the planar geometry. It's a bit so the sense in which this is a plane is it takes a bit of imagination, because just visualizing a plane is not enough, because it's not a stationary charge, it's a moving current, it's a moving charge. So you have to imagine a plane of current. I think one way to imagine it is to take this line of current and imagine that replicating that over some plane, so that you have a in one plane you have kind of line of current all moving in sync in one direction. So I think for my drawing here, I'm going to imagine that my plane is composed of these line currents that's going into and out of the plane that you see. Let me draw two views actually. For this line current, let me just draw a version. So this is like the side view, and I can draw a view where the current is coming out of the plane. And so for this line current coming out of the screen, you will have magnetic field that's going counterclockwise. So in this view, this is how the magnetic field looks like. And for the planar geometry, so if we imagine current that's flowing from left to right as it's doing in the cylindrical geometry, except there's many more cylinders both coming out of the plane and going into the plane, then in the first view that I drew, it doesn't really change, because it still looks like you have current that's flowing from left to right. Now, what changes is that in a view that looks like this, there's more than one line of current that's coming towards you. There's an infinite number of them extending quite a bit. I mean, when we say infinite, what we really mean in practical terms is extent that's much larger than any other relevant length scales, so that you can treat the size as being much larger than anything else. So in this geometry, I think as you look at this magnetic field and imagine how magnetic fields due to each individual contributions will add, you might get this sense that magnetic field above the current will point entirely to the left, and magnetic field below the current will point entirely to the right. And if you have that sense, that's great. That's how they look. And I think in a different lecture, I do a more detailed proof-oriented argument for that. And this is geometry has translational symmetry. You can see it in this picture, where if you move to left or right, the current distributions don't change, and magnetic field doesn't change either. And in this other view, where my current is flowing from left to right, it'll look like where above the plane, the magnetic field is coming out of the screen towards you, and below the plane, magnetic field is going away, going into the screen away from you. And unlike the picture on the left, there is a circle of magnetic field lines connecting the top and bottom. It's just separated. Okay, so those two are the geometries where you can draw parallel to what you have seen in electrostatics, and they have some, so there's some sense of familiarity to it, even though the direction of field looks very different from the electric field directions. Now, if you try to think of a parallel to spherical geometry, what you will see is there isn't one. Because, I mean, what does spherical current even look like? It's like trying to imagine a point current. And then you maybe think, okay, so you could have maybe a loop of current that goes like imagine you had a sphere of charge that's spinning. When you have a setup like that, some of the symmetries you had in Gauss's law application goes away, because if it's spinning, then there's now a special axis. So there isn't the same kind of rotational symmetry that you had for Gauss's law. You don't have that for magnetic field for Ampere's law, and that loss of symmetry is significant. So there isn't such a thing as a spherically symmetric geometry where we can apply Ampere's law. So we lose one geometry of some symmetry, but we actually gain two. There are two geometries where, when we are dealing with electrostatics and Gauss's law, we would have said there's no meaningful symmetry there, and we would have rejected it. But those now carry some meaningful, useful symmetry that we can use for applying Ampere's law. So let me list and illustrate those two geometries. So those two geometries are, and I'll just use the name that we'll be using for them. So this is the third geometry. There's a solenoid geometry. Don't know if a solenoid is just a pure geometry name or it's just referring to the device, whatever. I've only really used the term solenoid in referring to this kind of current geometry that works for generating magnetic fields. So I'll show that shortly. And the other geometry, and this one I know is a pure geometry term, a toroid geometry. And I think it's better seen than described, or I can describe it, but I think it'll be easier for you to imagine it if you see it. So I have a setup here that'll help me illustrate both solenoid and toroid geometry. I have a separate camera over here that's looking at things here. Okay, I gotta orient myself. Okay, so that's up. No, that's left. This is right. Okay. So this is an example of a solenoid. I mean, you might think, hey, isn't that just a cylinder? Well, it's a kind of a cylinder, but as you can see here in the center, it's wait, yeah, okay. In the center, it's empty. It's not filled cylinder, and a solenoid can't be a filled cylinder. And really, when we talk about solenoid, we are not referring to this cylindrical shape of the thing. We are referring to the wires that are wrapping around here. So I think you can see here, there's two leads to the wire that's going to these two leads. So when we are talking about solenoid, we are really talking about how the wire is wrapped around this cylindrical shell. So this wrapping around this cylinder is the solenoid. And I think for the solenoid symmetries that we are going to talk about, this kind of base of the cylinder has to be circular, so that it has a rotational symmetry about the axis that goes through it. And we are going to consider infinite solenoid. So this is not infinite, but we'll say for the one geometry we are considering, it's infinite. So it'll have translational symmetry. Because if this is infinite, then as you translate it, it shouldn't change. And I think that's it. Those are the two main symmetries that will be useful in figuring out direction of magnetic field and applying Ampere's law. So this is solenoid. And my toroid is, this is the example of toroid. Let me zoom in a little bit, because I guess the toroids I have are much smaller than the solenoid I have. Okay, so this would be an example of toroid geometry. If this reminds you of donut, it's not entirely wrong, but I think this is so this is a ferrite core that we use for electric circuits when we build inductors. Now, this ferrite core alone isn't giving you the full picture of a toroid. So really, this would be the example of a toroid that's complete. So when we talk about toroid, we mean we are referring to how this wire is wrapping around. So when we consider how this wire is wrapped around, that is the toroid. And ideally it would be uniformly wrapped, but this one I think, do I have something that's a bit better wrapped? On that toroid, I was just trying to wrap as many wires as possible. This looks a little bit more uniform. So for the purpose of our discussion, we'll assume that this wire is uniformly wrapped with a uniform density. So that's a toroid. And I think for a lot of the calculations we'll do, we'll imagine a toroid that looks exactly like this. As in, we'll consider a toroid where cross-sectional area, like if you imagine cutting this in half and looking at one face, one side of it, this one has a rectangular cross-section. And I think that's the most common toroid geometry we'll consider. Although the symmetries that we'll discuss for toroid, it's not limited to that, but rectangular cross-section makes it easier for certain calculations. But you could have a circular cross-section if you want it, or any other cross-section. So yeah, and with the toroid, the main symmetry that you have that turns out to be surprisingly useful is rotational symmetry. And really only one symmetry, which is a rotational symmetry about the axis that's now perpendicular to this face. So this rotational symmetry, you can see how as I rotate this toroid, nothing is really changing. So that one symmetry alone actually gives you quite a bit of simplification in figuring out the magnetic fields due to this object. So I need to show that. So let me just draw those geometries, solenoid and toroid geometry. So with the solenoid, it would look something like, let me have the solenoid be horizontally oriented. So if I'm describing the wire that's wrapping around, it would look something like, it would look, some circular thing. And I'm going to draw this as one wire that's wrapping around because that's quite common. But it doesn't have to be. You could actually, you can imagine solenoid as a infinite series of loops, very closely spaced together. If you treated it as that, that would not be wrong. Now, making all this one wire is simpler in some sense because if it's all one wire, I can make a single current I go through all the loops consistently. If you are independently controlling them, then that becomes a little bit hard. So this is a solenoid geometry. And as I was saying, it has symmetry with respect to rotation about an axis going through the center of the solenoid. So that's one symmetry it has. And there's a symmetry with respect to translation. And with those two symmetries in mind, the direction of magnetic field inside the solenoid, and let me just try to imagine it. Let me just fix this down. So at the top, the current is coming out of the screen. At the bottom, current is going into the screen. So when you do that, your magnetic field, this is the third right-hand rule, where you can use this either with a solenoid, or you can use this with a loop of current. So you wrap your forefingers in the direction of current that's in a loop, and your direction of your thumb gives you the direction of magnetic field at the center of the loop. So when I do this, then my thumb is pointing to the right, and that tells me that in the center of the solenoid, that magnetic field is mostly pointing to the right. And magnetic field up here is also pointing to the right. Magnetic field here is also pointing to the right. And outside the solenoid, and in the lecture, there's another video where we go through this argument in more detail. Outside the solenoid, if there were any magnetic field, it would have to point to left. This one, you just use your regular right-hand rule, or your intuition about how the magnetic field goes around the loop of current. So that's a solenoid geometry. And with the toroid geometry, so this is the hardest one to draw. That's why I opted to show this, so that, to the extent that my drawing is not perfect, you can imagine this. And as you imagine different perspectives of this three-dimensional object, that'll hopefully make up for any misleading things in my drawing. So let me just try to draw that in perspective view as best as I can. I'm just going to draw some rough outlines that I'll need to follow with this toroid geometry. Inner radius, outer radius, and I'll try to draw one with a rectangular cross section. So with this toroid, what's being referred to as toroid is not just, I think this is called annulus or donut. That's not the toroid. Toroid is how wire is wrapping around here. So let me wrap it so that at the top it's coming up into the top, and then it comes out this way, and then it wraps down at the bottom, and then it wraps around. And like with the solenoid, I can complete this as a loop and just imagine there being independent loops, but most common way we build these is with a single wire that wraps around this way. So something like that. Okay, my drawing is getting worse and worse. It's a quite three-dimensional shape, so it is hard to draw. You can imagine kind of a top view. So let me just indicate that this goes on forever, all the way around uniformly. And if you are imagining a top view might look like this. You have inner radius, outer radius, and along the inner radius, you'd have a current that's poking out of the surface, viewed from top. And each one of these currents that come up, they go outward along the top surface of the donut. And again, for our purposes, you have to imagine this being uniform. And along the outer radius, they go into the surface as viewed from top. They go down along the outer wall of the donut. And along the bottom, they wrap around and return so that it can wrap around. So in this geometry, you really have one significant symmetry, which is symmetry with respect to rotation about an axis that's going through the center of this. So there's a rotational symmetry there. And that rotational symmetry combined with your sense of direction of magnetic field for a loop of current, it'll tell you, so inside here, so let me try to use my right hand rule. So it's coming out of the screen. So magnetic field here will be pointed this way, and you can kind of connect it around. It goes in a circle. So this is the direction of magnetic field. Or drawing it in this top-down view, you'd have magnetic field that goes around in circle. And because it's there's that rotational symmetry, you can argue that magnetic field here and here have same magnitude and all that stuff. So this is the fourth geometry in which Ampere's law can be applied, or more specifically, Ampere's law can be used to calculate the magnetic field. So there's actually one more geometry in the application of Ampere's law than there was for Gauss's law. There's one more. Now, here's the good news. These four geometries are the only geometries where there is enough degree of symmetry that you can pull the magnetic field out of the integral and find it using Ampere's law. This is the comprehensive list. There's no other list where we can do the same. There's no any additional geometry where we can do the same thing. So yeah, so I say that's the upside, because this is the thing. In the lecture, you will see examples of application of Ampere's law using each of these four geometries. If you learn them all, then that's it. You've learned everything there is to know in applying Ampere's law.
So how did we approach these problems with electricity? So when we, so the calculational examples where we said, okay, even though in theory we can use Coulomb's law to work out these problems, this is way too difficult just mathematically. Do it using Coulomb's law. What did we do? So we used the symmetry, and the way we used the symmetry was we used it with the Gauss's law. So that's what I want to start thinking about as we cover Ampere's law. So because all the intuition you built up with the Gauss's law is going to apply to Ampere's law. So let me just remind you of Gauss's law. What Gauss's law said was this. So you calculate electric flux. You calculate electric field, dot product with some area element, and you add it all up for some closed surface. So you integrate over some closed surface. And what Gauss's law told you is that this quantity is equal to amount of charge enclosed times some constant, right? Let me ask you a couple of questions that I hope you remember the answers to. Is this law always true? As in, let's say you have this highly asymmetric situation where you have a dipole, let's say a positive charge and negative charge, and you try to apply this Gauss's law to a surface enclosing the negative charge. Can you still rely on this Gauss's law? Is Gauss's law still true? It is still true. Yeah, it is a fundamental law of nature. If you ever find a situation where this is untrue, you have, well, that's just not going to happen. It's like, it's just not going to happen. Science itself is wrong if that happened. So given that it's always true, what was the whole thing about the emphasis on symmetry? Like whether it's symmetric or not, this is still true. So why do we care about symmetry? To make the integral easier. So here the challenge is actually in the application, because this calculates the electric flux, but we don't care about electric flux. We don't care about electric flux. What we cared about was always the electric field. And when you look at Gauss's law, even though it's true, the electric field is always inside the integral. You have to find the situations where you can make the integral easy enough that you can actually pull this out of the integral without knowing the exact form of electric field. Then you could proceed to solve for the E and actually get the answer for electric field. That's the same thing we are going to do for magnetism, except it's not going to be Gauss's law because this was the fundamental law for electric field. For magnetism, we are going to use something called Ampere's law. So the relationship between Ampere's law and Biot-Savart's law, it's the same relationship, or it's the analogous relationship between Gauss's law and Coulomb's law. They both express the same thing. But Gauss's law was easier for calculating electric field when you have a highly symmetric charge distribution. It's going to be the same thing for Ampere's law. It expresses the exact same thing as Biot-Savart's law. It's equivalent to Biot-Savart's law, even though we are not going to prove that. But it will make it easier to calculate magnetic field for these situations. So let me write down Ampere's law so that you know what it is. I'll be writing this down quite a few more times now. So it's named after Ampere, the guy that we have a unit of current named after. So Ampere's law says this. You calculate what's called the line integral of magnetic field. So you have magnetic field, dot product with dl. It's exactly what it looks like. Dot product between a magnetic field and some length of I guess it's just any path that you define. So now, because it's a dl, I have to add it all up. I have to have some kind of path and imagining adding up all this quantity. And the kind of path that Ampere's law is valid for, it's a very specific type of path, we indicate it with this symbol. What kind of path do you think it must be? Closed path. So this is the difference between a closed path and a, well, not closed path. This path represented by this wire right now, that's not a closed path. I have a beginning and an end. So that's not a closed path. Closed path is the one that has no beginning and no end. So this is a closed path. It has no beginning, there's no starting point, and there's no ending point. Yeah. So I know it's a little bit too abstract, especially for lower division class. But this is how we define closed and open in topology. So when you have a closed surface has no boundary. When you have a, I don't know, I have no closed surfaces here. Well, this tennis ball, it has a closed path around it. Imagine you're standing on this tennis ball surface and ask yourself, where is the boundary of the surface? There is none. Once you poke a hole in it, then it's not a closed surface anymore, and the boundary is that hole. Okay? So it has to be an integral over the closed path, and we don't really have a name for this quantity other than that it's a line integral. It's exactly what it sounds like. And Ampere's law says that this line integral of magnetic field is equal to mu naught, a constant, times current enclosed. What does it mean for a closed path like this to enclose a current? I mean, how do you, imagine this is my current carrying wire. Like what would there's a big glare coming from there. What would it mean for this closed path to enclose the current? It doesn't mean it in the sense that you are used to describing it for Gauss's law. So for Gauss's law, it wasn't intuitively clear what it meant for charge to be enclosed. If you had this closed surface, enclosed charge would be inside the tennis ball. Not enclosed charge would be outside the tennis ball. But at least at an intuitive level, it's less clear what it means for this loop to enclose the current. Because it's not as though current will be like what is it even enclosing? So how would you, if you had to guess it intuitively, what would it mean for this current, which comes in from somewhere very far away and will go out to very far away, to be enclosed by this loop? That this would go around it, right? That's fairly intuitive, right? Yeah, and if you want to make this mathematically rigorous, this is what it means. This current, as it's going through some surfaces, right? We say that this current is enclosed if it's going through a surface, which is an open surface, which is bounded by this closed loop. So right now, you could say this closed loop is bounding a circle, right? And if this current goes through that circle, then it's an enclosed current. Yeah? We have to talk a little bit more about exactly the surface that this boundary is enclosing, but we'll do that discussion towards the end of the semester after your midterm 3. And it comes down to this. Let's see. The choice of the surface that this bounds, is that unique? As in, can you pick only one surface that this closed path is bounding, and that's it? You don't have to worry about there being any other surfaces that's being bounded by the same enclosed loop. Or is it the other way around, where given one loop, there's many, almost infinite number of surfaces that this could be enclosing? Let me draw this. So let me draw this side view here. If I have, so this is the side view of the loop that you're looking at, right? So imagine this. Like this is the side view of the loop that you're looking at. So the closed surface that I was describing and most of you are imagining is the path that's stretched over this as simply as possible. So that would be circle that's sort of bound entirely within it here, right? That's what you're imagining. But let me draw a slightly different picture. imagine that that circle. I start pushing on that surface. So I stretch it out to make that circle look something like this. So, it's almost like a balloon. So is this surface still bounded by this same loop? Or let me give you a more flexible surface so that it's easier for you to imagine. Balloon. So I have this balloon here. Can you tell me what's the path that enclosed the loop that bounds this open surface of a balloon? Like where is the boundary of the balloon? Yeah, the hole. This is the enclosed path. That's the boundary of the surface of a balloon. So right now the balloon that you're seeing is an example of one surface that's being bounded by this thing. What if, I'll have to ask you to just imagine it. So imagine I'm not pressing down on here, but this is all connected by a pipe. Is this surface still bounded by the same opening? Yeah, it is. So when you have a particular loop, it can bound many different surfaces. In fact, the simplest one here would be simply a circle that simply connects. But there's many different surfaces of different shape that still ends on the same boundary. And I don't want to spend too much time on it, but I'll just end with this saying that the fact that there's these many different surfaces that can have the same boundary, for the purpose of, there's the red surface that's bounded by this loop, the simple circular thing, and there's this green surface that's bounded by the same thing. For the purpose of Ampere's law, existence of this infinite number of boundaries, infinite number of open surfaces bounded by this loop is not a problem. Because you try to think of, okay, so you have this left-hand side, which doesn't depend on the surface, right-hand side, which might depend on the choice of surface, but you look at, okay, how could that choice of surface change my current enclosed? As in, imagine a current passing through this, passing through this red boundary. Could I somehow stretch out this surface in such a way that this current is no longer bound? This current no longer goes through this surface, even though it's going through the red surface. Like, is that arrangement possible? No, right? I mean, this current, it has to go somewhere. If it keeps going out to infinity, then at some point it's going to cross it. If it bends around, then it's going to cross it at some point here. If it bends around, makes a U-turn, and comes back out, then, so this enclosed current must be a net current. So if there's current going in and then out, then that doesn't count. Yeah? So I think in the couple minutes I have left, the exercise that I can go through, so I did want to go over the... So these are the 4 geometries where we can use Ampere's law to try to figure out the magnetic field. And the reason we couldn't start out with Ampere's law was that for you to have all this intuitive feel for the direction of magnetic field, you had to develop it using Biot-Savart's law. So all right, I guess we should actually do the calculation. All right, so this is the line current. I drew it vertically this time because that's easier. All right, so let's say we have a line current and we want to find the magnetic field due to this line current. We have done this using Biot-Savart's law before, so we at least know the result. The result that we get, if we do it correctly, it should be, let's see, mu naught I over 2 pi r. That's the result we had from before, right? So we are hoping that we'll get the same result using Ampere's law. But this will be a good setup to demonstrate how you apply Ampere's law. And I hope that this will look similar to with Gauss's law, because we have done the first step already similar to Gauss's law. We figured out the direction of the magnetic field. So when we have this line current, I know that my magnetic field lines in a perspective view looks kind of like this. So it'll be coming out of the board here into the board here. And this is how my magnetic field lines look like. Good? All right. So what do we do in applying Gauss's law to find the electric field after we draw the electric field lines? What did we do after having drawn the electric field lines? So, as a reminder, this was Gauss's law, right? The Gauss's law said the surface integral, or the electric flux, was equal to Q enclosed over epsilon naught. So even though we are not actually ever going to do an integral, we have to pretend that we are going to do an integral. So what did you have to do to set up that integral in applying Gauss's law to find the electric field? Choose a surface. Essentially, we have to define what we are integrating over here. So we have to choose what we called then Gaussian surface. So what we are going to have to do now is we are going to have to pick an Amperian loop. Amperian. By the way, I have seen Amperian spelled with the I here. That never felt right to me, so I'm just going to spell it with the E. So we have to pick an Amperian loop. It's a loop because we are doing the line integral, not surface integral. So remember how you picked the Gaussian surface. The goal in picking the Gaussian surface was that you wanted one or the other thing to be true for this E dot dA. You wanted either to be able to say that your electric field has the same magnitude over the surface due to symmetry. Or you wanted to be able to say that E dot dA is 0 for that particular surface, so that you could focus on the parts where it wasn't 0, right? All of that sounds familiar? So that's going to be our same criteria for choosing the loop here. So when we choose the loop, for the B dot dl, we want to be able to say magnetic field magnitude is same over the entire loop. Or we want to be able to say for particular line segments that B dot dl is going to be 0. Right? So here, this is a simple setup. So I think I can actually pick a loop, pick a path where the magnetic B dot dl will be uniform. It will be the same value of B over the entire loop. What shape would that loop be? It'll conform to cylindrical symmetry, but cylinder is a three-dimensional object. I'm looking for a one-dimensional object, a loop. Huh? Square is still a two-dimensional object. So circle, but not the circle, but boundary of a circle, right? Yeah, line is a one-dimensional object. So, okay. So let me refine my question first. So the question would have been, all right, pick a point here, P, and or pick a point which is at a distance R from the line. And the question would have been, what is the strength of magnetic field at this distance R? Right? So to answer this question, we pick an Amperian loop, for which we can say that this B dot dl will be constant around the loop. So the loop the path I'm going to pick is the circular path that goes through that point, so that the value of B I figure out has something to do with this point. Good? Any questions? So this is my Amperian loop. So like with application of Gauss's law, I would start by stating Ampere's law. So Ampere's law says that this line integral, B dot dl, around this, let me do this with red, around this loop that I defined in a way that it conforms to the symmetry is equal to mu naught times current enclosed. All right. Let me handle the left-hand side first. So what I want to be able to do is I want to be able to pull out two things. I want to be able to handle this dot product here. And after handling the dot product, I want to be able to pull out the magnitude of B. So what does this dot product look like for this path? So this is the question. The direction of magnetic field. Let's say pick a point here. Direction of magnetic field at this point, and compare that with the direction of dl. The direction of dl is the direction along the loop, right? How do they compare? How do those two directions compare? They're parallel, right? Which means I can simplify this dot product for it to be simply, well, just the line integral of B dl. Doesn't seem like I did much, but this is actually important. Going through this argument is important. All right, and now what I want to do is I want to be able to argue that the magnitude of magnetic field is constant over this loop. How can I, what do I use to make that argument? So how do I know that magnetic field at this point and magnetic field at this point have the same magnitude? Symmetry, what kind of symmetry? Well, you said the rotational, yeah. Rotational symmetry, you can imagine applying the rotational operation that will take this point to here, but you don't change anything physically, so they must have the same magnitude. So, make that argument. Once you have done that, once again, what you write down is really simple. But the actual mathematical argument you have to make are abstract, sophisticated. So you can pull out B. So you have B times the integral dl. Well, what is this integral of dl? Just the circumference of the circle, right? So just like with Gauss's law, we start by pretending that we are going to do some integral, and we are going to find some way not to do it. Because it's just going to be I don't actually have to do the integral. I know this is circumference 2 pi r. Yeah. Okay, so all of this is equal to the right-hand side. I guess I enclosed is just the current I. That's what's going through the loop. So this will be mu naught I. So they are equal to each other. And now I can solve this for B. So when I do that, I get magnetic field B is equal to mu naught I over 2 pi r. This is the exact same result we had using Biot-Savart's law. And just like with Gauss's law, the only difference was that this calculation was much easier. I mean, you do have to make a more sophisticated abstract argument. But once you are able to do that, then the rest of the calculation is much easier. Good? Questions? Comments? Okay, let's move on to something a little bit harder. So I want to do plane. I guess easiest thing to do is actually erase this line so that I have space here and use the space here. So I want to figure out what is the magnetic field due to plane of current. And I'm going to have to specify current density. And I don't know if there's a standard symbol for this, because it's not the usual current density where it's a current divided by area. I'm going to want current, the total amount of current, divided by some section, length of the length of the cross section of the plane. I don't think this is a standard symbol, but let me use this symbol. Due to plane of current density, sigma. And for the purpose of this question here, I will define this sigma to be amount of current per length. Good? All right, I'm pretty sure that's not the standard expression. All right. So we did the very first step, figuring out the direction of magnetic field. Now what I need to do is I need to pick a loop that exploits the symmetry that's shown in these magnetic field directions. So do you think I will be picking a circular path? No, right? Nothing here looks circular, so I'm not going to be picking circular path. And so I guess the nature of what this looks like is that whatever path I pick, I am not going to have my path always be parallel to the magnetic field. Because if I did that, the path never closes, it just goes out to infinity. And I can't do that. I have to, so this is a non-negotiable part. I have to have a closed loop. That's a non-negotiable part of applying Ampere's law. I have to close the loop. So any suggestions on what kind of path I should pick? Katie? No? I mean, I can get a start. So let's say I start at this point. Okay, let me do it this way. Let's say some question was asking, let's say I have a point here that says some distance d from the plane of the current. And somebody asked you, all right, let me call this distance actually, g, for the g-axis. And somebody asked you, what is the magnetic field at a distance g away? Like, that's the actual question. So let me get a start. Let me say, I start at some point here, move to the left along the direction of magnetic field, and make sure my path includes this point. Okay, what am I going to do? I can't just keep on going. That'll just take me to infinity. I have to have a plan for making this part of a closed loop. How am I going to close this loop? Yeah, I can go above. And when I turn at 90 degrees here and start going above, I hope you realize that that's actually okay. Because as I go at 90 degrees, this is 90 degrees. So any line integral from here is just going to be 0. I want to do this symmetrically. So based on a mirror symmetry, 180 degree rotational symmetry, I can argue that whatever strength of magnetic field here is, if I go same d distance above, then magnetic field strength here should be the same as magnetic field strength here. So let me go all the way up there, and then now go to the right, so that I can actually close this loop. So I pick this rectangular loop. And if you recall back to how we did this for Gauss's law, this is actually surprisingly similar. With the Gauss's law, we picked something that is a surface area, and connected in a kind of rectangular way. So this is like the lower dimensional version of that. So let's write down some things that I talked through as I was drawing it. So we said that the line integral here, b dot dl for this segment is equal to 0, right? We said b dot dl for this segment, we didn't say it, but it was implied. This is also equal to 0, right? Because it's at 90 degrees to the magnetic field. This is why it's so important to know the direction of magnetic field. So the only two segments I have to worry about are the segments 1 and 2. Yeah. So let's go through the motion. So I'm going to say Ampere's law. That's my starting point. So I have the line integral b dot dl is equal to mu naught I enclosed. And I'll say, all right, I broke this out into these 4 segments. 2 of the segments gave me 0 line integral. And the only segment that wasn't 0 is segments 1 and 2. So I can say this is the line integral for segment 1, b dot dl, plus line integral for segment 2, b dot dl. All right, where do I go from here? What can I say about the dot product? What does the dot product here look like it's going to do?
Parallel to each other?
It's parallel, so it also does nothing. BDL cosine theta is 1. So let me just get rid of the vector notation and say it's just going to be like a scalar product where I'm just multiplying their magnitudes together. Okay. Oh, I forgot to specify something. I knew I forgot something. I had to specify, so I know the height of this loop, 2g. I never specify the width. Right? So I need to specify the width. Let me just use a number. My hope is that this symbol will just cancel out eventually. So let me say this loop that I defined has the width w. And I'm hoping that it will cancel out in the end. Okay, I think I can do these two line integrals now. Line integral for 1 will be the strength of the magnetic field here times w. Right? So this is bw plus, what is the line integral for segment 2? Also bw, yeah. The path and magnetic field are going in the same direction. So it's plus bw also. And I've already made the argument that whatever magnetic field here is, B, it should be the same magnetic field magnitude here from symmetry. Yeah? All right, so the left-hand side is equal to 2BW. All right, I need to work out the right-hand side. So this is where it takes a little more work to figure out how much charge I'm enclosing. So in terms of the density, current density that we are using, how much current am I enclosing? Sorry, what? Not I over W. So I didn't specify actual current I because that would be infinite. When you have an infinite plane and you have a uniform current distribution, it's gonna. If I talk about I explicitly, it's gonna be infinite. That's why I'm talking about this density. How much current is flowing per some length of the cross section. So what would the expression for the enclosed current be? Okay, so the enclosed current is density times the length. Good? Okay, so the right-hand side is mu naught sigma W. All right, so from Ampere's law, we can say that these two are equal to each other. I see some things cancel, which is what I was hoping. W's cancel. So whatever this width of the loop was, doesn't matter because it cancels. So I solve for magnetic field. I get magnetic field is equal to mu naught sigma divided by 2. That looks familiar. Mu naught sigma divided by 2. Part of the reason it looks similar is, once again, I'm using the symbol sigma, which we used to use. It's a confusing symbol, sorry. So does any feature of this magnetic field look familiar to the feature you saw for electric field due to a plane of charge? What feature do you see here? Yeah, it doesn't depend on distance. So I started by pretending that magnetic field could depend on distance. So I didn't assume that magnetic field wouldn't depend on distance. But what this derivation is showing is that it doesn't depend on distance. So if I move this loop closer, then the line integral here wouldn't change. And so that's the feature you saw with the infinite plane of charge. So intuitively, you can use the same reasoning. Both the magnetism and electricity are inverse square laws. So when you have an infinite plane of stuff, no matter how far away you are still seeing the kind of same half sphere amount of the stuff, right? So, all right, and I guess the rest is kind of that. So the magnetic field doesn't have any distance dependence. It's just some constant times that. But once again, this is kind of a toy example. You would never generate magnetic field this way. Plane of charge was actually a physically useful model for capacitors and whatnot. But I can't imagine an actual physical thing that would have a plane of current somewhere. So it's a toy example that just illustrates how you pick your path so that you exploit the symmetry. And you exploit the portions of path where the line integral is going to be 0. Okay? Okay, I want to do solenoid at the very end. So let me do toroid next. Yeah. So we are going to look at magnetic field due to a toroid. The reason I want to do the solenoid next is the argument that I had to make for the solenoid is a little bit more obscure, sophisticated, or there's a very careful step you have to go through for solenoid that I don't think your textbook actually does. So you know, let me do that as long as it's my lecture. So let's do toroid. The toroid is actually easier, even though it's more complicated shape. So we are looking at magnetic field inside a toroid. And let me actually draw a top view. I think that's actually easier to illustrate what kind of path we are going to be dealing with. So let me draw the toroid in a top view. So it looks like, well, it'll look like concentric circles. The inner circle and the outer circle, right? So this is what I want you to imagine, top view of a toroid. Let me just specify some things here. If I look at some segment here, let's say current here would be coming out of the board, as in the wires, you know, going from the lower bottom to the top, and then go left to here, go into the board, and on the other side, it's going to go to the right to complete the loop. And then it'll, you know, come out here, go in here, and so on. And you know, it'll just continue on like this all the way around the toroid. Good? Yes, any questions? Okay, so this is the question that we could ask. Somebody could ask this question. What is the magnetic field inside the toroid at a point here? Let me give a couple things to characterize this point. It would be point at some distance r from the center of the toroid. And if I illustrate the point here, it would be, so you know, in this cross section, it can actually be any point here. So it could be like point here, as long as it's at distance r from the center. So this is the point P, where I want to figure out, well, what is the magnetic field at point P? Good? Okay. So how would you pick your Amperian, loop so that you can exploit the symmetry to calculate the magnetic field easily? What's the direction of magnetic field? I guess I forgot to draw it. In this top view, how does your magnetic field look like? It goes in, yeah, let's do that carefully. So, yeah, so here it's going downward, right? And it sort of loops around as it does. So it's a counterclockwise circular field. That's what you would see. Good? So I drew just one to illustrate the direction, but you have to imagine this at many different radii. So what kind of Amperian path would you pick? What Amperian loop would you pick to exploit your knowledge of the magnetic field direction?
I'm sorry, I'm not seeing how the right-hand rule.
Yeah, so you have to imagine this loop as a three-dimensional object.
Right.
Three-dimensional object. So current is coming out of the board here, going into the board here. Right? That's what this dot represents. Coming out of the board, into the board. All right, so I'm going to, this is the shortcut right-hand rule I'm using. I'm going to curl my finger in the direction of the loop. Out of the board, into the board. Then the thumb points in the direction of the magnetic field inside that loop. So downward.
Okay.
Yeah, and when you connect them, you get counterclockwise as seen from the top view. Yeah, so this is one of the challenging things about magnetism. You have to think three-dimensionally. And in so many of our physics classes, we kind of try to reduce it down to 2 dimensions. Magnetism is one place where you can't do that. All the cross products you see is an indication that magnetism has to be dealt with in three-dimensional space. Okay, so but my question still remains. What kind of Amperian loop should I pick? It's obvious, right? It's not some exotic shape. Not sphere. Once again, I'm looking for a one-dimensional object, a loop, a line that just loops back on itself. Yeah, circle, or the edge of a circle. Because when you say circle, it's unclear. Do you mean the two-dimensional object that is the circular area, or do you mean the one-dimensional object that's the boundary of the circle? So that's what it would be. Now, what I would have to be careful is to make sure that this circle includes that point. Otherwise, the line integral doesn't tell me anything about magnetic field at this point. All right, I feel like I've underspecified this toroid. Yeah, I actually have to tell, it's assumed that this toroid carries some amount of current I. And this is what I underspecified. I kind of have to tell you how many wires there are. So I have to tell you, so this is a finite object. It's not going to have an infinite number of loops. It's going to go finite number of time around. There will be finite number of loops it's going around. So I have to tell you how many times it goes around. So let me just say it goes around for n loops. So I had to give you this number before you can actually finish the calculation. Because you can imagine a toroid with a single loop would have a smaller magnetic field than a toroid with 100 loops. Okay. All right, so we picked the Amperian path. I think we are ready to get started with our usual calculation. As in, we are going to start up by pretending that we are going to do some kind of integral. So we write down Ampere's law. The integral of B dot dl is equal to mu naught I enclosed. All right. And we are going to start simplifying in a way that we never actually end up doing the integral that we are promising to. How does the left-hand side simplify? Yeah, you are one step ahead. I have to do one more step before that. I have to take care of vectors. I have this whole vector thing, and I cannot take out the vector magnetic field outside because that's not allowed. So I have to take care of this vector quantities and the vector dot product. So yeah, you have to make that argument. You have to make that argument that every single point around the loop, the direction of the loop, dl, and the direction of magnetic field are parallel. So you have to, it's a simple argument. Mathematically, it doesn't look like you are doing much. But if you skip this step, you have made an error in the proof, and everything else you are saying is wrong. And if you don't skip this step, then you have a chance of being right for the remainder of the proof. So you have to say, okay, they are parallel, so this dot product will simply end up being BDL for the entire loop. So once you have this, then now you can use something that you know about the magnitude of the magnetic field. That from the rotational symmetry, you can say the magnetic field magnitude here and here are the same. So it's the same all the way around the loop. So you can pull this out of the integral. You can say, oh, B doesn't have to live inside the integral. It can be out here. Once you have that, then this is a very simple integral. It's once again just the circumference of the circle that you picked. So this will simply be 2 pi r. This is beginning to look a lot like the line. I hope something's different. Okay, how do we express the amount of current being enclosed by this loop? So this is the loop. And by enclosing, really the question we are asking is how much I is going through this surface. How much current do you think is, how many units of current I do you think is going through this surface? Just one I, or more than that? Yeah, I times n. This is how it looks. I have this surface. The current pokes out through here, goes around here, and when it goes here, it's not poking through the surface. Goes around, pokes out again. So now it's done it twice, and then now it does it. It's done it 3 times. Keeps doing it until it does n loops. So the amount of current that's being enclosed on this in this loop, it's not just I, it's I times n, because it does that n times. So amount of current that's enclosed is n times I. Left-hand side is equal to right-hand side still. So I can simply solve for magnetic field B. So magnetic field B due to a toroid is equal to mu naught Ni over 2 pi r. Very simple. Nothing complicated. Now, if you imagine doing this calculation using Biot-Savart's law, as I said, I can't even imagine how you would set it up. It's just way too complicated. But using Ampere's law, it's actually pretty simple. Okay, I think I have enough time to finish the solenoid calculation. So let me redraw this solenoid over here vertically. So we are looking at what is the magnetic field due to a solenoid. So, I can specify a bunch of stuff about a solenoid. I guess the easiest thing to do is to imagine that you have this physical solenoid and sort of start imagining the kind of parameters that might be relevant. So, I have something that looks like this. I'll just draw it with a single wire. But for the purpose of our calculation, it doesn't actually matter if it's a single wire that's looping around a lot or it's multiple rings, the way I had drawn it before. So let me just draw some structure to indicate the geometry of the solenoid. So the solenoid, it'll look like something that's wound around the cylinder of capital radius r. And so let me wind it around this way. Here, it's coming out of the board. And each time it's wound around, so that here it's going into the board. Good? With this, let me draw the direction of the magnetic field that we figured out before. Magnetic field inside should point upward, direction-wise. And magnetic field outside, if there is any magnetic field outside, it should point downward. Good? Okay. All right. So there's the obvious current I that's flowing through the wire. And here's the one more thing I feel like I need to specify. Imagine you have a solenoid that has, this dense of wires, and imagine it's, half as dense. Like, do you imagine that will affect your magnetic field, right? So what I want to specify here is essentially the density of the loop. So let me specify it this way. If I take some length of solenoid, let's say for some length of solenoid, there are n loops. Or another way to say that would be the solenoid has a loop density. Or I could call this loop density of n, lowercase n, is equal to some number of loops per length of the solenoid. Right? Yes? Yeah, I want to it's specified as a density because I'm imagining this solenoid to be infinitely long. So unlike the toroid, the density is a better way to specify it. Otherwise, I have an infinite number of loops. Okay, so we've done a lot of the steps, a lot of the preliminary steps. So what's necessary here is choice of the loop. How you would choose a loop, Amperian loop, so that will allow you to calculate the magnetic field. So let me just say, all right, I want to know the magnetic field at this point. What is magnetic field here? That's my question. How would you pick the loop? Let's just start out with a loop that's going through this point. What would that look like? That's the easy part. Just straight line parallel to the magnetic field, right? That's how you should pick it. That's the easiest thing to do. So let me just pick it that way. So now I can just keep going forever. I have to close the loop. This is the one segment of the loop. So what I have to do is, all right, this loop is going to have some height h. And I have to think about a way how I'm going to close up this loop. Well, a lot of this reminds me of what I did for the plane of current. So I'm going to turn 90 degrees here, knowing that this 90 degrees here will give me 0, the line integral. But this is where I run into difficulty here. So I can, come in from outside and go outside. And this is the question: how am I going to close it here? Do I have some symmetry that lets me say that the magnetic field outside is same as the magnetic field inside? You don't have that. With a plane, you had a 180-degree rotational symmetry. Here, inside and outside are very different. Point that's inside here and point that's outside here, that's very different. There's no transformation that will take one point to the other. So this is the point that your textbook just skirts over. They just say magnetic field outside is 0. So let me show you the set of steps that will allow you to prove that magnetic field outside is actually 0. This is what I'm going to do. I don't quite know how to close this loop, so I'm just going to imagine keep going. I'm just going to keep going, knowing that I do have to close it at some point. But I can keep going forever because this length of the segment here, it's not accumulating any line integral of b. So I can keep going without any consequence. And when I come out far enough, I imagine that, okay, I came out far enough, now I'm actually going to close this loop. How far do you think is far enough? Like if I write down what this distance r is, what do you think that r should be? I'm going to let this r go to infinity. And letting this r go to infinity is far enough for a particular criterion. And that particular criterion is at this point here where it's arbitrarily far away from the solenoid, I can say my magnetic field here is actually 0. Or as r goes to infinity, magnetic field goes to 0. How do I know that? This is what I would imagine. Imagine this is an infinitely long solenoid. So when I'm near it, it looks like a solenoid. Imagine stepping very, very far away from it. As you step far away, what does it look like? Not a point. It's an infinitely long solenoid. Oh, it looks like a line of current, right? What did a line of current what did the magnetic field due to a line of current look like? How did it change as a distance? Yeah, so 2 pi, I don't care. Divide 1 over r. Yeah, so that's the actual relationship. The magnetic field should go as 1 over r. That's the result that we know from previous derivations. So we know that magnetic field will go to 0 as r goes to infinity. So this is my loop. It's not something that you can draw on a finite surface, but this is how I'm going to start. So, well, let me do the calculation then. So I only have a couple minutes left, so let me just kind of hurry through this calculation. So the calculation I would imagine doing is, okay, write down Ampere's law, B dot dl is equal to mu naught I enclosed. All right, so I have 4 distinct segments to think about, right? Segment 1, 2, 3, 4. What's B dot dl for segments 2, 3, and 4? 0 for each individual one of them. Because it's perpendicular, because magnetic field is 0, and because it's perpendicular again. So this integral just comes down to a line integral over segment 1, which would be the magnetic field that we are trying to find. And we already argued that it's a uniform along this distance, right? Yes? So magnetic field we are trying to find times the height. So it would be B times the height of this loop. That's equal to mu naught times how much current am I enclosing? Height times lowercase n times I, right? Yeah, so it'll be h and I. Okay, h cancels out, good. That's sort of what I was hoping for. So this is the result I get using this loop. Magnetic field inside the solenoid is equal to mu naught and I. It's a pretty simple result, and we are actually going to be using it from time to time. And this is the argument I want to make, to say I want to actually argue two different things. One, I want to argue that the magnetic field inside the solenoid is uniform. Does this support that? Right? This expression has no dependence on where this segment is. It can be in the center, it can be on the side, as long as you don't go across the current. As you move the segment around, nothing changes. What that means is the magnetic field inside the solenoid must be uniform. And I can actually imagine doing the same thing with this segment here. So I had to study this out at infinity because I had to know that this segment will contribute zero contribution to the line integral. But imagine that I deform my loop this way. I'm going to bring this in from infinity so that this now looks like this. Instead of this segment being way out than infinity, it's going to have some finite distance. When I do that, does anything on the right-hand side change? No, amount of current I'm enclosing still hasn't changed. On the left-hand side, does this line integral change? No, that didn't change, which means there's no room for this line integral to be anything other than 0. It has to be 0. There's no other value it can possibly be. In fact, that statement is true all the way up until this point, until you actually cross this. Which means because this line integral has to be 0 by all the other things I constrained, that means, well, here it's also still 0. This is the proof that the magnetic field just outside the solenoid is 0. Unlike magnetic field just outside the loop, which is not 0. Yes. It's a surprising result. I'll just say that much. So I want to play the lecture video, the first 2 minutes of it, and I want to use the section of the textbook to talk about what kind of considerations go into in working with magnetism in matter. So, you've seen this work as an electromagnet, right? But when you actually look at it, it's not a very strong electromagnet. So I have this steel ball here, which I can attempt to pick up using this electromagnet. And I will, put through maximum current like I did before, after this cools down a little bit. The thing is with the wires heating up, it's a vicious cycle. The more it heats up, the resistance increases. So anyways. So now let me turn on the magnetic field to the maximum possible. And when I try to pick this up, I can't really pick it up. But you have seen me actually pick up the steel ball before, right? How did I do that then? Like if this magnet is right now strong enough. You might not remember how I did it. Do you know, have you seen electromagnets, that like practical electromagnets people use? Is it really literally just a coil of wire, or are there other parts to a practical electromagnet?
Other parts.
Okay, what are the other parts?
Flat, like a metal flat
Well, if it has a ferromagnet, then it's not an electromagnet.
Or like another, like, sort of another piece of like iron.
There's another piece of iron. It's the iron core. So this is I think it's a ferromagnetic. I don't know exactly what it is, but it does stick to magnets. So I think it's at least the ferromagnetic. So I have a ferromagnetic material, and when I put it in here, and so right now it doesn't work because this is not an actual magnet. It's just a piece of iron or something close to it. But once I turn on the current, now the magnetic field will be strong enough to actually pick this up. So let's try that. So turn it on. Yeah, now it's strong enough to pick it up fairly easily. In fact, I can go down in current quite a bit before it drops the ball. Okay. Yeah, I only needed something like 1 ampere of current, a third of the current that I was using to pick up this ball. So what happened? Why is the magnetic field now stronger?
I think that's about where, so, that demonstration, that's a little bit too much work to set up for this Zoom session. I want you to play that to show in practical uses where you really have to consider magnetism in matter, not just magnetism in vacuum. So what you see in the video clip is that for something simple like electromagnet, you have to use a ferromagnetic core. And later on, when we do the AC circuit or time-dependent circuit, when you see inductor, you will see that the inductor also uses the ferromagnetic core material. If you just try to form something like a solenoid with nothing in it, then it doesn't really work well. So because in practical uses of magnetism, that's where the properties of magnetic materials come in. I want you to make sure that we cover that so that we're not leaving significant gaps in something that you ought to know if you are dealing with the magnetism later. So this is the last section in chapter 12. So magnetism in matter gets potentially complicated. Let me contrast it with electricity in matter. So we talked about electricity in matter when we talked about capacitor with a dielectric or molecular model of a dielectric. So this is basically electricity in matter. And the reason we covered this was so that we have something to compare to when we do the magnetic materials. I realized this. The first time I taught physics 4B, I actually skipped this material thinking, hey, not that important. You'll cover this in upper division. But when we got to magnetism and we needed to talk about magnetism with magnetic materials, that we didn't have this convenient analogy to electricity. So we did talk about dielectric, particularly when we were talking about capacitor, and there's the kind of material picture of how dielectrics affect operation of something like a capacitor plate, and this is how it works. So in this picture, the dielectric reduces the electric field in between the plates, so it increases the capacitance of the capacitor because you are storing the same amount of charge with a smaller voltage difference between the plates. Now, with the magnetic matter, things get a little bit more complicated. When we were dealing with the electricity in matter, dielectric was basically the only thing we talked about. This model of how dielectric works, that's basically it. This describes basically every single insulator, and we are done. We don't really have to worry so much. To the extent that things respond in a linear way, this is how you would describe it. With the magnetic matter, the textbook already tells you about 3 different types of magnetic material. It's right at the top here. Paramagnetic material, diamagnetic material, and ferromagnetic material. And what I have to lead with is that Within classical physics, we don't really have good explanations or derivations for magnetic properties of material. To explain each of these properties, how they come about, you need quantum mechanics. So in this session, I'm not going to attempt to explain why ferromagnetic material is ferromagnetic, other than that it is, and what parameters we use to characterize these materials. So now, paramagnetism tends to be fairly weak. So you have some alignment of the magnetic dipole moments in a material along the direction of magnetic field, and the effect of that tends to be relatively weak. So this portion, read through it, work through it. Now, where I want to draw the comparison to is here. So when as they finish the derivation for the magnetic field of an infinite solenoid, this expression here is with a solenoid with a vacuum, with no magnetic material inside. So this mu naught is the permeability of a free space. So again, accepting that the word permeability is old-fashioned term that applies to some sort of magnetic property. Free space refers to vacuum. So what this constant describes is the magnetic property of the vacuum. And with this polarizability, what you can describe is just the permeability of materials. So this I can just refer to as permeability of whatever material it is we are dealing with. So the effect of the magnetic material is that wherever you have this constant permeability of free space, you can kind of replace it with another constant. Oftentimes, that constant represents the magnetic property of the material. And if you're dealing with a paramagnetic material, then this chi would be some number bigger than 0. So this mu would be greater than mu naught, and it'll tend to enhance the magnetic field inside the solenoid. And I think the most common magnetic material we find use for is a ferromagnetic material. And I guess I need to skip over the diagram. So this chi, it tends to be relatively small value for a lot of these paramagnetic materials. You know, a lot of metals, oxygen is famously paramagnetic. With the ferromagnetic material, you can talk about some kind of polarization, and it tends to be fairly strong. There's something about magnetic domain that I'm not going to attempt to explain. And if you work out what the effective value of polarizability is, it turns out to be pretty high, 6 times 10 to the 3 well, as a typical value. Compare that with the constant for the paramagnetism. The oxygen, even liquid oxygen, which is fairly paramagnetic, is 3.5 times 10 to the minus 3. So it's about a million times more polarizable than some of the most paramagnetic material. And with the ferromagnetic materials, you will see that your textbook doesn't give you a table of polarizability. That's because it's not quite linear. So in fact, it also exhibits hysteresis, which we won't really get into. You can read about it. It's a fairly interesting effect. So this is kind of quick-ish overview of magnetic materials. One thing I would point out is I kind of skipped over the diamagnetism. I think diamagnetism, once again, all 3 effects, paramagnetism, diamagnetism, ferromagnetism, there is no good way to explain them classically. All of them requires some bit of quantum mechanics to fully explain it. I think what we did in the conceptual questions for paramagnetism is as close as we can get without explicitly invoking quantum mechanics and particle properties. And later on, Oh, actually in 1 week, we'll be in a better place to talk about diamagnetic materials when we have talked about Faraday's law and electromagnetic induction and Lenz's law. So I'll reserve discussion of diamagnetism until then. And even then, it's again not a full explanation of diamagnetism. You need to bring in quantum mechanics for any full explanation of magnetic properties. So this is the overview lecture on magnetic materials